What's up, ladies and gentlemen? This video is intended to help you with inclines. And we're going to start off by discussing why the free body diagram is what it is for the free body diagram, and then we'll do a sample problem, which is somewhere between definitely not easy and definitely not evil, but a really solid test problem. So let's start with a free body diagram, okay? And we're going to go right now for the simplest, so no friction. But we have gravity. Now, I'm going to draw this gravity long for a reason. It's to help with the diagram to come. So this is going to be Fg, which is equal to mg. And then we have the normal force, which is always perpendicular to the surface. So it's not up. Normal force is not, quote, up. It is perpendicular. That means 90 degrees to the surface. And our surface is inclined. All year, the x-axis has been horizontal because of the fact that our surface that we've been dealing with is also horizontal. So the x-axis has matched the surface, and our y-axis has always been perpendicular to the surface that we're on. So now we have a surface that's inclined, and therefore our x-axis, parallel to the surface, our y-axis, perpendicular to the surface. We went over this in class, but we'll do it again here. Here's the issue. Normal force is directly in the y-axis, but gravity is somewhere between x and y. This is the new thing. We have literally rotated our coordinate axis, and gravity is no longer in the y-axis. It's between x and y. And we went around and we said if this is theta here, and this is 90 degrees here, and this angle in here is 90 minus theta. And if that's 90 minus theta and this is 90 degrees, then this angle here is theta. What that means is, theta equals theta, but if this angle at the bottom is 30 degrees, the angle of the incline, then this angle here is also 30 degrees. Okay, so now we've said that that little angle between the y-axis and the force of gravity is actually the same as the incline. And, as per usual, we usually take forces that are in both the x and the y and break them into their horizontal and vertical components. But this time it's not horizontal and vertical, it's x and y at angles. Good times. So we have gravity in the y, which I'm going to call Fgy, opposite of Fn. And then we also have Fgx, which is parallel to the incline, not to the right. People tend to draw it to the right, but it's, see, incline, Fgx. They are parallel to each other, okay? Other classes may call this Fg parallel and perpendicular. That's fine. I like those names as well. But the purpose in doing this is to help us get a relationship between what's going on here in this triangle here, all right? And to make it a little bit easier so you can see it, I'm going to redraw it on the side. Some of you may not need this, but you can fast forward through it. So I'm going to draw this on the side where this is mg. That's the force of gravity. We've called this Fgy. And we've called the bottom one Fgx, parallel to the incline. And theta at the top. Okay, we want to relate these sides using trig. Mg is the hypotenuse. It is the longest side of the triangle. It's opposite the 90 degrees. So what trig function relates Fgx, which is opposite from the angle, to the hypotenuse? Well, opposite should be screaming sine at you. So sine theta is opposite hypotenuse. So that's Fgx over mg, or the force of gravity in the x-axis is simply mg sine theta. Yes, I realize that for most of the year, x-axis has been cosine. However, in those cases, the angle is touching the x-axis. And in this case, the angle is touching the y-axis. Basically, whatever angle axis the angle is touching will be cosine. And speaking of which, check it out. Fgy is adjacent to the angle. That means cosine. So cosine theta would be adjacent over hypotenuse, or The force of gravity in the y-axis is mg cosine theta. Now, you will not be asked to derive this again, but you will no doubt memorize these things, not because you're going to sit there and study them, but just by pure use doing incline problems. You'll be doing FGX, FGY, like no big deal. Okay. I do have some recommendations when it comes to drawing the free body diagram. Your base free body diagram for an incline, I would suggest doing FN, perpendicular to the surface. FGX is down the hill. Notice I've drawn it directly on the box, the object, and FGY is opposite FN, okay? If the incline was faced this way, again, Fn is perpendicular to the surface. FGX, literally the force of gravity in the x-axis. Please don't say it's to the right. That is the worst thing you can say. It's down the hill. If we drew FGX to the right, are you saying that gravity pushes things uphill? Because if you are, okay, you may want to be tested for drugs. I don't know. But last time I checked, gravity doesn't push uphill. And FGY is opposite FN. And I draw, like people say, which triangle should I draw? And I tend to make sure the object is moving to the right. So in this case, I have the object going downhill. And for this one on the right here, I am pretending the object is going uphill. That's how I see it. But either way, notice my arrow is pointing to the right, towards the positive x-axis. Please trust me on this. It'll help with sign errors. If you don't want to do it, you don't have to do it. All right, let's get after solving an actual problem now that we have reviewed how to draw the free body diagram. This is somewhere, I think it's on a review maybe it's a homework, but we have a snowboarder being pulled up an incline. And yes, there is friction. We could have started with a very simple example where there's no friction, but please, that's beneath you. You are physics machines. You don't need that. Here we go. Here's my snowboarder. My artistic ability is out of control, amazing. Let's draw that free body diagram. We do have a 400 Newton force, this force of the rope, a tow rope, pulling this up the hill. So this tension force is 400 Newtons being pulled up a hill. We have the normal force, which is the force of the surface, perpendicular to the surface. We have the force of gravity in the y-axis, which again is mg, cosine theta. That was terrible. And then you have FGX down the hill, and FG in the x-axis is mg sine theta. Let's do this right. And because this is a pretty good problem, there's also a little bit of friction here. I see the coefficient of friction. So friction acts opposite the direction it's sliding. So this is the force of friction. And I guess I should throw the angle in here before I forget, 12 degrees. Terrific. So step 1, draw a free body diagram. Step 2, as you know, is sum the forces in the x, sum the forces in the y, do a little kinematics. Nothing's changed after that. This is a regular dynamics problem. And some of you, you might want to start with the y so that you get the normal force right away. And that's okay. Again, if you're not comfortable with that, just start with the forces in the x. There's a reason I'm about to do what I'm going to do. I'm going to set this up algebraically. I'm going to sum the forces in the x that cause the mass to accelerate in the x. I have the tension force up the hill. I have FGX down the hill, which is mg sine theta. We have the friction force, which is down the hill, which is mu Fn equals, and that's it. Those are the forces, the three forces in the x, equals max. I'm going to quickly do the forces in the y here so we can get the normal force. I'm going to do that over here. Sum of the forces in the y that cause the mass to accelerate in the y-axis. Little thing about this. People say, oh, it's going up or down the hill. Yes, that's true, but remember, this is your x-axis. And the object never leaves the x-axis. Therefore, how could it accelerate in the y-axis if it never leaves the x-axis? So the AY is 0. And here we're just getting that Fn is in the positive direction, and FGY, which is mg cosine theta, is in the negative direction. That adds up to near 0 newtons, excuse me. So like most friction problems, I've isolated Fn, and I plan on subbing it in all the way over here. So let's do that. Again, there's a reason I'm doing this. Ft minus mg sine theta minus mu times the normal, which is mg cosine theta, equals max. Okay. We do a lot of problems where mass does divide out. And the tendency here, like algebraically looking, just like, oh yeah, let's just cross out the mass. Easy there. Easy excited person about crossing out mass. Is there a mass in every single term? The answer is no. You know why? Because all I see is tension, and there's no mass in there. If this tension wasn't here, is there a mass in every term? Yep. Would the mass divide out? Yep. But not in this case. So that's the reason I did it algebraically. I just, sometimes mass divides out, sometimes it doesn't. If you know by now, the rule is if it's only normal gravity and friction, mass will divide out. If there's any other external force, like a tension or a person pushing or pulling, mass is not going to divide out. Anyway, let's sub in some numbers and see where that takes us. I'm going to scroll down here because I don't have a lot of room. 75, 12, and 0.2. Let's see how well we can do this. So scrolling here, because it's going to be a long equation. We have 400 newtons acting to the right minus a 75 kilogram person acted upon by gravity at an angle of 12 degrees minus mu times the normal force, which is mg cosine theta. Mg cosine of 12 degrees causes this 75 kilogram snowboarder to accelerate up the hill. Woohoo! And if we solve for acceleration here, we get that the acceleration is 1.38 meters per second squared. Yippee! All right. I think that's where this problem ends. It says, what is the acceleration of the snowboarder up the mountain? But by now, you are seasoned professionals when it comes to dynamics problems. Most of you probably don't even watch this video unless you love the entertainment value it provides. Go to sleep to this. I don't know what I'm talking about. I just had a cup of coffee, a little amped up. So anyway, point is, we may need to connect to kinematics. In this case, we didn't because it directly asked for acceleration, but maybe you'll have to do some kinematics. Or you do a little kinematics first to get the acceleration, which you could then plug back in or sub back into the some of the forces that cause it to accelerate. But don't forget, it's a dynamics problem. We connect back to kinematics all the time. All right, let's do a quick review before you pass out. From excitement, oh God, I'm a terrible, terrible loser. All right, in general, we have that you should draw a free body diagram, forces X, forces Y, and kinematics. It's a standard dynamics problem. By now, if you don't know that, let me know, and I'll educate you. And the free body diagram, your base free body diagram that you see I've drawn like in this area here, if it's going uphill, that's how I draw it. I always just make sure it's going to the right. So uphill to the right, downhill to the right. Your base FBD is always FN, perpendicular to the incline. FGY, directly opposite FN. And FGX, down the hill for all that is good and holy. Please make it go down the hill. People are like, well, I thought it's right. It's not right. It's down the hill. How does gravity act right? It acts down. I don't know. Maybe you're in another universe. Oh, look at that. In green. I'm not even paying attention. FGX is always parallel to the incline and down the incline. I think I made my point. FGY is always perpendicular to the incline and opposite FN. And side note, if we do a multi-part with an incline, which we will do, the final velocity of part 1 is equal to the initial velocity of part 2, and vice versa. We've done this many times. Multi-part problems are not new for us. So I have examples here. We can go down an incline on a horizontal, or across a horizontal and then go up an incline. Or we can go down an incline, up an incline. Or we can go up an incline, down an incline. There's so many options. Can we make bunk beds? So much more room for activities. Anyway, if you get that reference, cool points for you. as for this video, I hope it was helpful in some way, shape, or form. And I would give it a rock solid 3 out of 5 stars. Wouldn't change a thing.